Hey, Lucas.
Hello?
Yeah, how you doing?
Hi. Good, how are you?
Good. So, it's amazing how long computers take to reboot anymore, isn't it?
Yeah.
I'm wondering what's going to happen in 100 years, because as long as I've been alive since they've had computers, every year it takes longer and longer to reboot them. So, what does that mean? It'll take an hour to reboot in 50 years? I don't know. So, what are we working on today?
Alright, well I have a couple things that I was like getting held up on.
Okay.
So the first one was finding the derivative using the definition
Okay.
of the derivative.
Uh-huh.
And the function was 8 over x plus 2.
Okay, the definition for first derivative.
I have it to 8 over x plus h plus 2.
Well, it's f of x plus h minus f of x all over h, and the limit of that as h goes to 0.
Mm-hmm.
So, if we plug in, what's f of x plus h?
8 over x plus h plus 2.
What's f of x?
8 over x plus 2 over 8.
All right.
Yeah.
These problems, all they are, is complicated algebra problems. In other words, what we always have to do next here is perform this subtraction. What's the common denominator?
X squared.
Well, let's leave it unmultiplied. In other words, let's leave it like this.
Okay.
That's the common denominator. What goes up left?
8x plus 2.
And on the right?
X plus h plus 2.
And all of it's being divided by h. Now, when we distribute this, we're going to discover that all of the terms without h disappear. So our new numerator becomes 8x plus 16 minus 8x minus 8h minus 16 all over x plus 2 all over x plus h plus 2 all over h. Well, and this always happens no matter what the function is that every term that does not have an h in it disappears. And notice what I have. I have 8h left in the numerator. Well, that h cancels with that h. So now we're left with taking the limit of 1 over x plus 2 times x plus h plus 2 as h goes to 0. And what is that limit equal to?
The h in the numerator canceled with the h in the variable.
Yeah, if you have a fraction, in other words, we had minus 8h over x plus 2 times x plus h plus 2, all divided by h. Well, that h in the denominator is in the numerator of the denominator. In other words, it's really h over 1. So in order to divide that, we flip it and multiply, and the h's cancel. And we're left, we're left with an 8. I left out the 8 here.
Yeah.
In fact, it's minus 8.
Would it be negative 8?
Minus 8, sorry. So what is the limit of this as h goes to 0? Just plug in h goes to 0. Plug in 0 for h.
So that would be -8 over x squared plus 4.
Well, you don't need to multiply it out, and it's almost better not to multiply it out. It just becomes x plus 2 times x plus 2 in the denominator.
Yeah.
Okay. Now, if we go back and we look at doing it the easy way, that was our function, right?
Yeah.
Apply the power rule. What do you get?
You get -8 x plus 2 to the -2.
Which is what we got. That's what this is right here.
Okay.
I'm not quite sure why they insist upon starting you off in calculus with the toughest way to do derivatives, which is by this limit definition. And
well, that was
tough just because the algebra is tough. What's that?
That was the only problem on the worksheet that I have, that you use the definition.
Yeah. Yeah. Once you get past that part of calculus and you get into the power rule, have you had the product rule, the quotient rule, the chain rule yet?
No.
Just had just the power rule?
Yeah.
In other words, what's the derivative of that?
Yeah.
What's y prime here?
It's 12x to the 12x cubed.
Right. Now, when you get things like this, you can't use the power rule.
Mm-hmm.
You have to use something called the product rule. And you'll learn that. That's coming up very shortly for you.
Yeah.
And if you have something like this, you have to use the quotient rule. And if you have something like this, you have to use the product rule and the chain rule. So all of these rules will allow you to easily differentiate functions. Much easier than using the limit quotient definition.
Yeah.
But still not, I mean, you can differentiate most any function using one of those 4 rules. When you get to integration, it's a completely different story. Integration is the inverse of differentiation. So whatever this is, in other words, the derivative of that always equals that. That's integration is the inverse of differentiation. You can apply the power rule in reverse. But when you get problems like this, that is a bear. I don't even know how to integrate that. There are lots of functions that integration becomes almost impossible, and you have to approximate the answer or put it into your computer or calculator and do it. But let's not get ahead of ourselves. Just that's the nature of differential calculus, is you're going to end up with 4 rules that are going to allow you to differentiate pretty much any function you can think of.
Yeah.
What other problems would you like to go over?
The next one is find the definite integral by computing the area using the average of LRAM and RRAM.
Okay.
The function is square root of 16 minus x squared.
And we want the area from where to where?
From -4 to 4.
Well, we know that the integral of a function is the area between the function and the x-axis. Now, let's just get an idea of what this thing looks like. Might be useful. What was it? The square root of 16 minus x squared?
Yeah.
All right, so there's the function. And we want the area under that curve from -4 to 4. And they want you to do it the hard way, because the easy way is just to integrate it. In other words, that's what integral is the area under the curve.
Yeah.
They want you to approximate it. Do they tell you what size intervals they want you to use?
It says 3 sub-intervals.
3 intervals?
Well, it says 3 sub-intervals.
3 sub-intervals.
Yeah.
Hold on one moment. Hello? Sorry about that. All right, well that's a little peculiar because we're going from -4 to 4, which doesn't divide into 3 intervals. In other words, there's a total of 8 there.
Yeah.
Sure they said 3 intervals?
Well, it says approximation to the estimated area of unit graph function, blah, blah, blah. Using the indicated number of sub-intervals. And then the only one that has a sub-interval has the 3 sub-intervals.
Doesn't make any, do you see why it makes no sense to use sub-intervals of 3?
Yeah.
It would use 4. Let's do it with 4, and then we'll go from there, regardless of what your problem is. It doesn't make sense to do it with 3 intervals. So first thing we can see from this graph is that it's symmetrical. So let's just do the right side, and whatever we find out this area to be, we're going to double it. Okay? So let's talk about left ram, and I'm going to divide this thing up into 4 intervals. If I use left ram, this is what my rectangles look like. Now, the key here is we have to find the area of each rectangle. Let's call this rectangle 1. What is the height of rectangle 1?
It's f of x is 1.
It's f of 0.
Or f of 1.
It's f of 0. We're using left ram.
Yeah, that's true. Yeah.
Okay. So the height of number 1 is f of 0 times 1, the base. Right? What is f of 0 equal to?
4.
Rectangle number 2. What's the height of that rectangle?
Square root of 12.
Make sure that you use this point as the height. And a very important leap here is that that number, the height of that, is f of 1.
Yeah, I look at 2 and it's
So the area, the height of 2 is the function evaluated at 1 times its base. Well, what's f of 1 equal to?
14.
Square root of 15.
Oh, square root of
Plug in 1 for x. Rectangle number 3.
is the square root of 12.
That's f of 2 times 1, which in this case is, we'll just leave it at square root of 12. We won't worry about simplifying it at the moment. And finally, rectangle number 4 is f of 3 times 1, which is square root of 7. So the area using left ram this is interesting. I've never experimented with left ram to the left of the y-axis before. I still think might be different, actually. Now, let's talk about just this area to the right of the y-axis for the moment. We've just approximated it using left ram. What do we get? We got 4 plus root 15 plus root 12 plus root 7. So there's our answer. 4 plus root 15 plus root 12 plus root 7. That is the area from the y-axis under that curve to 4, to its x-intercept. Okay, now let's go back and look at right ram. The first rectangle that I'm going to draw, there's the top of it.
Yeah.
What's the area of that rectangle?
Square root of 15.
Do it in terms of f. It's f of what? And this is an important leap to make because it's fundamental to all of calculus. Is this height is f of 1. F of 1 was root 15. So we have root 15 as the area of the right ram rectangle in that interval. What's this area? Or what's this height of rectangle number 2? F of what?
F of 2.
Yeah. In other words, that right-hand corner of the rectangle has to be on the function. So that would be f of 2, which is square root of 12 times 1. The third rectangle is f of 3, which is square root of 7. But we have a fourth rectangle that has no height. So the area of this part of that function by right ram is this, less than this, by a significant amount. And you would expect that. You can see by looking at the way I've drawn it that the right ram method underestimates the area under that curve, and the left ram method overestimates it. Now, it isn't always that way. It depends on the shape of the curve. But when you have a curve that's going down like this, it's going to be like that. So when they say compare the areas, well, if I was just comparing this area here, then the left ram method is 4 more than the right ram method. Now, if I want to consider the left side of the equation, or the left side of that graph, because it's going the other way, let's see, if I consider the left side, yeah, the left ram method on the left side gives you the same count as the right ram method does on the right side.
Yeah.
So the left ram method, the first rectangle has a 0 height. Second rectangle has a height of square root of 7. The third rectangle has a height of square root of 12. And the fourth rectangle has a height of square root of 15. So if you want the area of this left ram versus right ram, it's going to be the same area. Because as we go to the left side of this equation, the left ram underestimates it and the right ram overestimates it by the same amounts that it is in reverse on the right side of the y-axis. So if they want, in other words, what I'm trying to say is the left ram is going to give you the same number as the right ram if you go from -4 to 4.
Yeah.
So there's no difference. If you were going from 0 to 4, there would be a significant difference. It would be a difference of 4.
Mm-hmm.
There's also mid-ram. Have you studied mid-ram yet?
No, but isn't that what you just used?
Mid-ram, what would the height of the first rectangle be using mid-ram? F of what?
F of 0.5.
F of 0.5, exactly. In other words, there's your first rectangle right there. Its height is going to be F of 0.5. It's going to look like that. And we can see from the picture that mid-ram looks like it would work better than left ram or right ram. Because part of that rectangle is underneath the curve, part of it's above the curve. That should be a pretty good estimate of the area, mid-ram. And then the second rectangle is going to have a height of F of 1.5. So forth and so on. Now, I haven't seen very many calculus courses that make you deal with left ram and right ram to the left of the y-axis. It's only today that I think I've ever tried it. And I see that to the left ram underestimates it by the same amount that it overestimates it on the right. So using one or the other, as long as I'm going from -4 to 4, should give you the same answer, whether you use left ram, right ram, or mid ram.
Yeah.
However, the way I was originally going to do it, which was to take this area and multiply it by 2, doesn't work on this particular problem because when you use left ram to the left or to the right of the y-axis, it does the opposite things. One overestimates it, one underestimates it.
Yeah.
All right. What else you got?
Alright, the next one is the same, finding the integral.
Okay.
But the function is kx plus 1. And then it's between 0 and 1.
Okay.
And k is greater than 0.
What kind of function is this? Linear. Going through the y-intercept at 1 with a slope of k. Going from 0, we'll make 1 over there. And they want you to do the same thing. They want you to use left ram and right ram.
Yeah.
Now this one we could divide into 3 intervals because we're dividing 0 to 1. You know, the last one we were going from -4 to 4. It doesn't make sense to put 3 intervals in there. You're dealing with oddball fractional numbers on the x-axis. But this one, let's use 2 intervals or 3. I don't know. We'll try 3 intervals on this one. So the first interval is at 1/3. Second interval is at 2/3. Using left ram, what's the height of my first rectangle?
F of 1/3.
Yeah.
Oh no, F of 0.
Yes, f of 0. In other words, if I'm using left ram, I have to make the top left corner of the rectangle be on the left side and lie on the function. So there's my first rectangle. Here's my second rectangle. Here's my third rectangle. So the first rectangle, the area of number 1 is 1/3. Well, let's do it this way. It's f of 0 times 1/3, the base of it. What's f of 0? Or what's this equal to?
F of 0 is equal to 1.
Okay, times 1/3. So that area of that rectangle is 1/3. It's the area of the second rectangle, which would be f of 1 would be its height.
It would be 1/3. It would be function f of 1/3, not f of 1.
Excuse me. You're right. And f of 1/3 is k over 3. Ooh. F of 1/3 is k over 3 plus 1. But then we have to multiply that by 1/3. So we get k over 9 plus 1/3. There's the area of rectangle number 2.
Wait, what? Oh.
Because remember we're solving for the area of a rectangle, so we have to multiply it by the base also.
Yeah.
And rectangle number 3 is f of 2/3 times 1/3. Well, f of 2/3 is 2k over 3 plus 1 times 1/3, which is 2k over 9 plus 1/3. So the 3 things I have circled there are the area of the 3 rectangles. Let's do right ram over here. And I'm going to use blue pen. Where's the first rectangle? What's the height of the first rectangle using right ram?
It's 1/3.
So it's the same as this one here, which we figured out was k over 9 plus 1/3. So that's rectangle number 1. Rectangle number 2 would be the bottom one on the left, which is 2k over 9 plus 1/3. And rectangle 3, I want to make sure that that is the rectangle. In other words, I start by making the upper right corner of the rectangle fall on the curve.
Yeah.
There's your 3 rectangles for right ram. And this one is f of 1, which is just k plus 1 times 1/3, so it's k over 3 plus 1/3. So what is that? 15k over 9 plus 1. This is 15k over 9 plus 1 for a total area. And this one is the sum of the first. It's 1/3 plus k over 9 plus 4k over, or plus 2k over 9. So that's 3k over 9. So it's 1/3 plus 1/3 k plus 1. So this one is 2k over 3 plus 1. And this one is 15k over 9 plus 1. Now, in point of fact, we're looking at a straight line, which means we don't need calculus to do this. We can use geometry. We're looking at a trapezoid.
Yeah.
And we know how to figure the area of a trapezoid.
Yeah.
What you need calculus for is to figure out the area under curved lines, where we don't have geometry that we can use. All right. Does that answer that question fully?
Yeah.
Okay. Again, this is a painful way to be introduced into integral calculus.
Yeah.
Because once you get past this, you don't ever use left ram, right ram, or mid ram again. Because we have techniques that are so much better.
Mm-hmm.
Have you had the trapezoidal method yet?
Well, he didn't be doing much integral calculus until next year.
There's another method that's better than left ram, right ram, or mid ram. And that's the trapezoidal method, where instead of drawing rectangles, I draw trapezoids. In other words, the top of that thing fits the curve a little bit better. And you can see that this is going to be a much more exact approximation. It's just that in order to figure out the area of this trapezoid, you need f of 1, you need f of 0, and you're going to need f of 2, f of 3, f of 4, and f of 5, if we've made it into 5 partitions. But trapezoidal is better than left ram or right ram, and there's one final method, which is what most calculators use. And that is called Simpsons Method, where the very top of that thing is not a straight line, it's a parabola. In other words, if instead of putting a rectangle or a trapezoid here, I make this a parabola at the top, in other words, a curved line, now if I can figure out the area under that parabolic shaped thing there, that's the most accurate method of all.
Yeah.
And that's the one that uses what's called Simpsons rule. And in fact, when you use your calculator, all calculators use different algorithms, but a lot of them will use Simpsons rule, which means they're using parabolas at the top.
Yeah.
What else you got?
Okay, the next one is summation notation stuff.
Okay.
And the first four, these like values of the function are 5, 10, 20, and 40.
I'm not quite hearing what you're saying, Lucas. Can you speak up a little?
The first four values are 5, 10, 20, and 40. And then it's just dot, 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 so it goes to infinity, but it says right in
Sigma,
summation.
in sigma format.
Yeah.
Okay, what kind of series is this?
It's arithmetic. Or no, geometric.
Each term is separated by a common multiple, not a common difference. In other words, I'm multiplying everything by 2. So let's see if we can come up with a number here. How about 5 times 2 to the n power, where n goes from 0 to infinity. Does that work?
Yeah.
Yeah, it does, doesn't it? Only reason I know that. And incidentally, these are not unique. I could also write it like this. If I insisted upon going from 1 to infinity, then I would have to write this as 5 times 2 to the n minus 1. This is the same series as that. You'll notice.
Yeah.
Where n starts is kind of based on the function. In other words, if I had a function like this, log of n, where would n have to start?
N would have to start at 2.
Yeah, because the log of 1 is 0, and I'd be dividing by 0. So there's no way I could start at 1. I'd have to start it at 2. So that's usually determined by the type of function you have. In other words, you can't have any of your terms being infinite. Okay. The only reason I knew that last one is because I had a problem like that yesterday with a student, and I had a little difficulty coming up with it. And after I hung up with him, I worked on it for about 10 minutes and came up with it and realized how to do it. You got to use a little bit of creativity when you do these. There's no automatic formula for coming up with this. The sigma notation.
Yeah.
It's kind of trial and error. You come up with something and you see if that produces that series. And if it does, you got it right. If it doesn't, you go back and work on it more. Do you have any more like that?
Well, the other one was much easier. I already got that done.
Okay. There's some series that are a little strange. If I gave you this series here, believe it or not, that series is 2n minus 1.
Yeah.
And so you kind of learn some of that. In other words, you learn the series 1357 is 2n minus 1. Because coming up with that on your own would be hard. I'm not sure I could do it if I didn't know it already. I mean, I would experiment with a bunch of different things, and finally I might happen upon that, and yeah, that produces that series. But coming up with it without knowing it in advance, that can be a little tough.
All right. Well, the other one I had trouble with, the last one I had was another integral one.
Okay.
And it's cosine x plus 7.
Like that, or cosine x in parentheses like that?
No, it's all, the cosine x plus 7 is all in parentheses. Yeah.
I gather you have not. Have you learned the derivatives of trig functions yet?
No. Well, this one would be negative sine.
No, just positive sign. In other words, That's sine of x plus 7. If you took the derivative of sine, you get cosine. If you take the derivative of cosine, you get negative sine. But if you take the derivative of sine, you get cosine. Remember, we're going opposite here. In other words, whatever the integral of this is, I better find out that the derivative of that is what I started with. And in this case, it is. So we know that's the answer, but what do they want you to do with it?
Well, my teacher did tell us that the area under of cosine and sine curves, just under one curve, is 2.
Is what?
Is 2 pi.
You're talking about this area here?
No, the entire, like...
There's the cosine curve and the sine curve.
Yeah. If you... No, but, like, each hump on the sine and cosine curve has an area of 2 pi.
Oh, okay. Yeah. In other words, if I just had the sine curve there, that's pi. So if I want the area of that, I'm going to take the integral of the sine of x dx, and I'm going to go from 0 to pi. Well, the integral of that is minus cosine of x, evaluated from 0 to pi. Well, cosine of pi is minus 1. So this is 1 minus the cosine of 0, which is 1, which is minus 1. So it's 1 minus a minus 1. That's 2. So that area is 2.
Yeah. So since the graph is shifted up 7.
Well, now hold on. The x plus 7 is inside the parentheses, unless the 7 is outside.
No, it's inside.
Okay. So that plus 7 is a horizontal shift to the left of 7. In other words, that's a phase shift, basically. So I would start the curve here at minus 7. Well, let's draw the cosine curve, first of all, instead of the sine curve. What we just did was the sine curve. Let's erase that because we don't know what that is yet. So our curve looks like the cosine starting right there.
Yeah.
Minus 7 is close to 2 pi. So I almost have to begin and end this curve by the time I get back to there.
Yeah.
Now, how do they want you to get the area of this thing by left ram, right ram stuff?
Well, it says compute the definite integral.
Okay, from what limit to what limit?
From negative pi over 2 to pi over 2.
All right. Do they tell you how they want you to do it? You don't know integrals of trig functions, or you do?
Well, this one would be sine x.
Sine of x plus 7, evaluated from minus pi over 2 to pi over 2.
Okay, so sine would be 7 at...
Well, hold on. if we do this evaluation, we get the following. It's the sine of pi over 2 plus 7 minus the sine of minus pi over 2 plus 7.
Yeah.
Whatever that answer is your answer. Now, this, I guess you can put that into a calculator to figure out what the sine of pi over 2 plus 7 is. This becomes 7 minus pi over 2. Oh, hold it. Yeah. I mean, what's unusual about this problem is the fact that, see, it seems to me like that 7 should be outside the parentheses, not inside. You sure it's inside?
Yeah, it's inside on the
Okay, because if it was outside, then the antiderivative of this becomes sine of x plus 7x. It matters a lot whether it's inside or outside. The only reason it's puzzling that it's inside is because it's in numerical format. It doesn't appear to be in pi format of any kind. In other words, we're adding 7 to pi over 2 when we evaluate it, which certainly can be done. If I go into Wolfram Alpha, it'll give me an answer for that. If I type sine of pi over 2 plus 7, let's see what we get. Sine of pi divided by 2 plus 7. Look at how long it's taken to do it. Wow. Why would it take that long to do it? Interesting. Now I know that my computer is very, GoToMeeting uses a lot of my RAM, but it doesn't want to do this, does it? Finally gave me something, but whether it's going to be a result or not, yeah, there it is. Ah, same as the cosine of 7. It's 0.7539. So it can be done this way. You got to be a little careful. When I said the antiderivative of cosine of x plus 7 is sine of x plus 7, that is true. But if I said, what is the integral of cosine of 2x, that's a different story. That's going to be the sine of 2x divided by 2. In other words, if you take the derivative of that using the chain rule, which you haven't even had yet, how can you not have had the chain rule and yet you're doing integration? You must have been through the product rule quotient. No, they're teaching calculus to you strange. In other words, they're not going through all of differential calculus before they get to integral calculus.
Yeah, they're not.
But this is not automatic when you're integrating. It's not clear at all how you get that, but that's what it is.
Yeah.
All right, well, I guess that's a good place to stop. Got any last questions?
No.
Okay, I will talk to you next Wednesday, Lucas.
All right.
Bye-bye.